So let's discuss now the idea of vectors. Let's just start from the most fundamental. Approaching vectors, there's three ways that you could approach it. You could approach it from the mathematical, which is of course the orthodox way, through algebra, but that's usually a little bit too complicated for the purpose of using vectors in physics, but any more specifically in Physics 2053. There's another way of approaching it, which is from the applications point of view, which will be through computer science. What are vectors in computer science? Which of course, if you have started programming, you have found vectors and matrices, which are vectors of vectors, so to speak, right? And if you are approaching it from physics, which is also an applied point of view, and remember that in physics we use just mathematical tools to express the modeling of nature that we're building, right, quantitatively, which is the quantitative science, that is the science that studies the quantitative aspects of objects in motion. Then we're going to use the mathematics to take care of that quantitative, but at the end of the day we're referring to physical systems, to things that exist in reality, right? So from that physics perspective, we're going to also introduce vectors, and just to answer the question from physics point of view, vectors are going to be arrows. So that's basically it. But let's start from the point of view of mathematics to try to understand where is this coming from and maybe helping us understand better what this thing of vectors is. Let's say that you're at the beginning, like 10,000 years ago or whatever, or 5,000 years ago. In any case, you are in a situation where you have a storeroom or warehouse, and then you're accounting for people in your bookkeeping, right? And then you realize that some people maybe deposit one banana, some people deposit two, someone deposits five, and you start counting things, and then you use, of course, the numbers that will be the natural numbers, which of course are going to be 1, 2, 3, 4, and so forth, right? You're counting things, how many things are in there, and this is the trivial approximation of a number. A number is just a quantity, and we're counting stuff. But at some point you might realize that someone doesn't have anything. Maybe they exhausted all the resources, so they have 0. And at some point even they might have been borrowing from other people's storage, right? So they own them. And then we start to count for those things, not just the 1, 2, 3, or 4, but as -1, -2, -3. So all those numbers we of course call the integers, right? So in the integers we're going to have -5, -3, and all the way to 0, and 1, 2, 3, blah, 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 right? So we have an idea here of numbers that has been generalized. So we cannot have a minus something. It doesn't make any sense, and 0 doesn't really exist as such. But what we're doing here is just reflecting a reality where we have generalized counting stuff to something superior. And this is constantly happening in mathematics. You generalize ideas to go to more abstracts from first principles that either are arbitrary and they're just axiomatic definitions, or actually reflecting, as historically in this case, reflect realities, right? And you can go beyond this because, for instance, if you're sharing a pizza with your friends and the pizza is cut in 4 portions, then you're going to take 1 out of those 4 portions, and then you use a ratio or a rational number to describe that situation, right? And in your rational number, it's going to be, let's say you're taking 1 of 2 parts, or maybe you're taking 5 or 7 of 7 parts, and you can build here whatever you want. In fact, you could even say, I own 1 of 2 parts to someone, and obviously 0, etc. So you have rational numbers, which are numbers that of course can be defined as a ratio meaning a fraction. And there are numbers, of course, that cannot be described as ratio. For instance, that's the case of pi, that's the case of e, the Euler number, that's the case of the Aurea proportion, that's the case of a square root of 2. Those numbers never end, so they have infinite decimals if you wish, and you cannot write them in the form of a fraction of 2 integers. And in that case, then you need something more. And then we can generalize the concept of number to include all the this is q actually, all the real numbers, right? And that now, yeah, that contains -5, it contains 1/2, it contains pi, it contains e, it contains many different numbers, right? But they realized at some point that this is not enough. Why? Because mathematically you might be solving an equation to solve for a variable, and that variable might be necessary to be input in another equation to continue in calculation. And you find out situations such as that you end up having that the square root of 2, let's say, is equal to -1. And then you stop saying it doesn't make sense. Why? Because if you solve for this, you're going to say that the x is equal to the square root of -1. But what number multiplied times itself can give you -1? None, because if you take 1 times 1 is 1, but -1 times -1 is also 1. So no number multiplied by itself is going to give you an imaginary, a negative number. So this is sort of an imaginary number, right? And we call that I. And this is at the source, of course, of the complex numbers. So in complex numbers that we can call the complex numbers, we're going to have numbers that are composed out of a real part and an imaginary part. This is the real part, and this is the imaginary part. And why is this important? Is because this allows us to save this problem and maybe then use an equation that later on the function is going to be a function of x, and we're going to find that eventually x is going to be x squared at some point. So we just lose. If we had a stop here, we wouldn't find that actually this is going to be 1, for instance. And this is a physical variable, right? So this might be complex or might be imaginary, but at the end ends up taking the real part. And this is used, for instance, in advanced physics if you're doing, for instance, circuit analysis with the polar way of disconnected circuits and so forth. This is, of course, beyond the goal of physics 2053, but what's relevant here is that at some point in history they generalized even beyond what's real to what we call imaginary and to what's complex, which is made out of real and imaginary. But think about this. Now we're saying that this is a number, but this number, if I add two complex numbers, let's say Z1 it's equal to 1 plus 1i, and Z2 it's equal to 3 plus 2i, if I want to know Z1 plus Z2, what I need to do is add together the real parts and add together the imaginary parts. And what I find is 4 plus 3i. So in a way, this column or this real part and this imaginary don't talk to each other. They don't affect each other. They're completely independent. And so you can make a geometric interpretation of this and then say, oh, look at this. I'm going to have here the real part, and I'm going to plot here my imaginary part. And you go to 1, 1, and then you say this is this number over here. You go to 3, 2, and then you go like 1, 2, 3, and then 2 would be like something like that. And that's the 2, right? And then you can figure out the stuff in here. I don't want to go into detail, but basically this is the goal, at the core of the idea of vectors, historically and conceptually. What's happening here? My numbers are not anymore composed of a single number. It's not 2, it's 1/2, it's pi, is anything. Now my number is composed of 2 numbers. So I don't have enough just 1, 1, I need 2. And this is at the idea, it is at the core of the idea that we're having with vectors. In vectors are collections of numbers, they're going to be ordered collections of numbers, and those numbers were going to be very functional to us or very useful to us in physics. Let's see how they're used actually in computer science quickly, and then we jump to physics. So computer science originally started somehow like a way of automatizing tasks that could be performed repetitively and mechanically, right, with machines. So basically we wanted to automatize information gathering. Let it be through databases or let it be through calculations. So let's say that you are recording or trying to create a database of students of your class, and you want to include a number that identifies the students. Let's say a number that identifies the student, we could call an ID number. Then you're going to also write their age, and then you're going to write, for instance, their height, right? And you write this on an index card. The idea of a vector here is that it is an ordered list of numbers. This is made of 1, 2, and 3 numbers. And these 3 numbers in my space are always going to be in this order: ID, age, height. You could make the index card starting with age, going to height, and ending with ID, or any other permutation that you wish. That's not relevant. What's important is once you fix that, this order needs to be respected. And so you're going to build for an entire class. Each one of those guys are going to have their own ID and their own cards, etc., right? And so you're going to collect all the indices, all the index cards where you have written all the information. So you put this on a drawer, for instance, you have your database, an old-fashioned database. And then someone asks you, by the way, what's the average age, for instance, of the students in your class? And what you have to do is go one by one by index cards and taking them together and reading. But reading what information? Only the second. So if we call the index card V, for instance, V for vector, right? If V, we're going to see it's equal actually to a list of 3 numbers, which is one number here, which we could call, let's say, N1, N2, and N3, where N1 is ID, all right? This is ID, age, and height. So if I wanted to find the average height of all the students, I would have to go first index card, take it, read it, this one, and so forth. So how can I do that? In reality, what I'm doing is summing up, and in math we use this symbol, this sigma, capital sigma, to represent a sum. All of the students, let's say from 1 to n, let's imagine that we have n total students, right? This will be second student, third student, and so forth. So I want to add from 1 to n, what? Each one of the vectors that this describes the student, and times here, what? Times here, 2. And what is this? The position of the information I'm trying to gather. And when I do, and of course I divide times the number of total of students, then I'm going to have the average age, right? Average age. So this is what I do basically. I'm going to take this vector plus this vector, and I'm going to put them, and I'm going to add them all together, only accessing the second position of that vector. That's why it's important that the list is ordered. If it's ordered, then I can access the second position in all the vectors, add them together and calculate the average. If this was randomly placed, then I would have to go to the first index card, find out what's the position of the h, and write it down, and then go to the second one and find out what's the h, and so forth. But once we have an organized way, we actually can operate with them very easily. And this is the idea for vectors. As from the computer science perspective, they hold, or they're like boxes where you're putting information, but those boxes are ordered in a particular way, and that's why it's very relevant. So now we have this, we have the number as a generalization from the mathematics perspective, we have a vector as a list of ordered quantities. We can go now to the vectors from the physical perspective and see how actually all of them overlap and explain the same thing, because it's at the end of the day the same instrument or the same object, mathematical object, but it's going to be more interesting for us from the point of view of physics. Let's say that you are building your own physics as we're doing in this course, and at some point you come up with a magnitude or a quantity that you want to describe, that is, for instance, the temperature of an object, and you have come up with a way that you can actually measure the temperature. For instance, what's the height of a mercury column with this and that. Okay, that's all good. And so what you can do next is, of course, once you have that idea you want to express, you can associate it a number, right? And so if we're talking about temperature, we're going to say, oh, well, the temperature of this object is going to be 3, it's going to be 5, it's going to be whatever it is, 55, I don't know, whatever it is, right? But we have a single number to express this temperature, whichever it is. But let's say now that instead of actually describing the temperature, you're describing, for instance, something like velocity. And then you say, well, I'm going from home to, from Orlando to Miami. Right, so let's pretend that this is Florida, kind of, after a horrible hurricane. And what we're saying is we want to go from Orlando to Miami, right? Now, this is a very important thing. It's not the same thing to go Orlando to Miami, that go from Miami to Orlando. And in fact, it's not the same if I'm taking an airplane and I take off and I'm the pilot. It's not the same if I'm going in the direction south, or if I'm going north, or if I'm going east, or if I'm going west, or if I'm going north of east, or any other combination. I see that even if I'm going at the velocity of the airplane, 500, 400 miles per hour, whatever, right? I do not have enough just telling how fast I'm going. I need to tell them also in which direction I'm going. So now we have the idea of a vector. And what is a vector in physics? For us, vectors in physics, well, vector is a number that has two things. It has a magnitude and it has a direction. So we need to have this to be able to contain all the information that we require. And then typically we write them with a small arrow ahead on top of. Sometimes in the book you're going to find that this is bold to distinguish it from just simply numbers. This we call vectors, and this we call scalars. And it will become obvious why in a second. But these are just purely numbers, which only one number and contains the entire idea of the quantity that I'm trying to represent, but vectors do not have enough with a single number. This is very similar to the idea of the complex numbers. In complex numbers, I don't have enough just to say the real or imaginary part. I need to represent both. In vectors, we're going to see that depending on the dimension of the vector on space, I'm going to have enough with 2. If I was on a volume, I would on a plane is 2. If I was on a volume, I will need 3. And if I was in hyperspace, I will need n, the n being the dimension of that hyperspace, right? We're not going to deal with those in physics 2053. We just are content to work in 2 dimensions, or all our vectors are going to be 2-dimensional. But the idea of a vector still remains. It's not enough to describe this quantity, just giving a number being, for instance, the strength or the magnitude of that velocity. For instance, if it's the wind, oh, the wind is 100 miles per hour, yeah, but in which direction? If the wind is coming against you, or it's coming for you, or it's coming sideways, it's different. You have to prepare. Let's say you're in a boat or you're in an airplane. You want to avoid turbulences. You need to know how the wind is blowing. So it's not enough to know how much is the strength of the wind. You actually need to know the direction. So all those magnitudes in physics, such as velocity, such as acceleration, such as displacement, such as forces, those require a vector because they have both a magnitude and a direction. And what's going to be interesting is we're going to see that vectors also geometrically can be represented as arrows. And that's important because once we understand that, we're going to be able to also see how to graphically add them together and understand more of the concepts. The magnitude is going to be defined by the length of the arrow, right? The length of the arrow is going to give me the magnitude. And the direction is going to be given by where is the arrowhead pointing to. So of course, this vector and this vector even if they have the same length, they have different direction because the arrow is pointing somewhere else. And these two vectors, for instance, have the same direction, but because the arrow is pointing in the same place, but they have different length. Again, this is the idea. This will be like 10 miles per hour blowing south. This is 100 miles per hour blowing south. So it's different. I want to capture that. How do I capture it? Let's draw an arrow. And how we draw the arrow on our physics problems is by, of course, always starting by drawing our axis of coordinates with respect to which everything is included. And then what we're going to say is that the arrow is going to have a length and a magnitude. And typically we say the length and the length of the magnitude, let's say this is the vector, right? The length is going to be given simply by the length of the arrow, but the magnitude is given by this is going to be the length or the magnitude, which we're going to call v here, which is the modulus of v, and there's going to be a direction that we can call theta if we want, which is the elevation over the x-axis, over the horizontal, by definition, but you could define another theta. I just don't recommend you to do so. Let's use the standard, and we're all good. So, what happens when I do this? Then I remember SOHCAHTOA, and if I want to know the vector, I can represent the vector as going towards the right on the x-axis, and then going towards the on the y-axis, or I could do the opposite. I could go from the y and then go to the x. It doesn't matter. At the end of the day, I can describe this as two motions happening or two increments happening in the x and y direction. So in fact, I can define my vector as vector in the x component and the vector in the y component. So now we see indeed we need two numbers. We keep them ordered so we can operate with them, which is the idea of computer science, and they represent quantities as a generalization of a number from mathematics. But there's something interesting here. Because I can draw this, I can use geometry. And geometry, remember in SOHCAHTOA, I can see that Vy, which is this side of this right triangle, is actually going to be given, is the opposite, so it's SOHCAHTOA. So SO is for the opposite, Ka is cosine adjacent, so this is the sine. And you're going to see that this is sine theta is actually opposite, which is V sub y divided by hypotenuse, which is the modulus. And so Vy is going to be modulus of v time of sine of theta. And we could do something similar with the cosine of theta, which is going to be the adjacent because it's so it's Ka adjacent. The adjacent of this angle is Vx divided by v, and so I'm going to have that, of course, Vx it's equal to the modulus of v times cosine of theta. So let's rewrite quickly these two things. So we have that the vector can be defined as two components, one x and one component in y, and those components are actually going to be the modulus times cosine theta and the modulus times sine of theta. So indeed I see I have the direction and then I have the modulus. There's another way of saying this also. Because this is a right triangle, instead of theta and theta, I can do the opposite. I can say how much is v? Well, if I call this vx, I have side and hypotenuse on a right triangle. So of course, the square of the diagonal, which is the hypotenuse, it's equal to the sum of the sides square. And so of course, if I solve for v, I'm going to find that this is just the square root of vx squared plus Vy squared. And even I could use SOHCAHTOA and then use TOA to realize, I'll write it here, that TOA, it tells me that the tangent of theta is TOA, so it's opposite divided by adjunct. What's the opposite? V sub y. What's the adjacent, V sub x. So what is theta? Well, it's the arctank, right? The arctangent of V sub y divided by V sub x. So again, I contain the same information by giving the length and the magnitude, which is the length, which is v, modulus of v, and the magnitude, the magnitude or the direction. I can define the vector, or I can use it in the x and y components. And this is what we call vector decomposition. That's all there is in vector decomposition, pretty much all that we need to know. Let's see some operations with vectors. But at the end of the day, before that, one more comment on vectors and space. But at the end of the day, this is exactly all that we want to do. We want to have vectors. We realize that the vectors in 2 dimensions are going to be described as two numbers to define the same single magnitude, right? Magnitude of temperature was a single number. Magnitude of velocity is going to require two numbers. One is going to tell you a number in the horizontal component. One is going to tell us a number in the vertical component. And so that's the idea here that we're trying to do. Every time we're going to have a vector, we're going to split it in two. And as we know from, or as we will see in 2-dimensional motion, that can be described, any motion in 2 dimensions can be described as a horizontal component and a vertical component. So the first thing that you will always do in a 2-dimensional problem, as you will see in two-dimensional problems, is actually describe the vector into the two components by means of using this equation, and then just use them independently for describing the horizontal and describing the vertical motion. Let's see operations with vectors. The first thing we're going to do is adding vectors. So that's what we can call vector addition, right? So let's say addition. So let's say that you want to write the number A is going to be 3 and a number B is going to be 5. And then we're going to compare that actually to a vector which is going to be given by two components. Let's work in two dimensions. And we're going to call this 3, 2, and vector B is going to be -1, 3. Or let's say +1, 3 for the time being, okay? So how do we operate with this? When you have A and B and you ask how much is C, which is the addition of the two, of course, you know that 3 plus 5 is the same as 8, but you also realize that C plus A plus B is the same as B plus A, so the operation is commutative, and so it's the same as 5 plus 3, which is of course 8. Is this respected in vectors? It is. So if I define now a vector C and I'm using C with the arrow to represent this vector, and I'm saying that that's just A plus B, I need to know that's the same as B plus A. The operation is commutative, and actually the result is just going to be given as adding together each one of the components. So in this case will be, we can write it first in terms of components. So the sum is going to be A sub x, which is the x component of A, and B sub x plus B sub x because it's an addition, comma, because that's the first number, the second number is going to be A sub y plus B sub y. So in this case it will be 3 plus 1, 2 plus 3. 3 plus 1 is 4, 2 plus 3 is 5. There's nothing more with vectors, addition. You just add individually the components, all the horizontal together, all the vertical together, all the x together, all the y together, and that's it. Interestingly, because vectors can be represented as arrows, we can always draw our space again with x and y, our coordinates, and represent these vectors. And we can say that this vector is represented as, let's put 1, 2, 3, go 1, 2, 3, right? And so let's say number is 3, 2, so I have to go 1, 2, 3 in x, and 2 in y, so I go 1 and 2. So this is the first one. This is vector A. Well, that's the point that begs. To make it a vector, I need to go from here all the way up to there. And how much is that? Well, if this is a triangle, of course you know that this is how much? This is 3, of course. This is the component AX, which just said that. And how much is this? This is A sub y, which of course is 2, 1 and 2. How much is the hypotenuse? Well, the hypotenuse is the modulus of the vector. So that's the square root of ax squared plus ay squared. And how much is that? That's ax squared is 9, and ay squared is going to be 4. So that's going to be the square root of 13. And how much is theta? Theta is going to be the arctangent of what? A sub y, which is 2 divided by 3. So I can find the magnitude and I can find the direction, or I can describe the vector as these components, and there's no more trouble. Okay, that's for A. We could do the same about y, B. Let's write it directly. We go 1 on x, and we go 1, 2, 3 in y, and this is number, this is number B. So what is the problem now? We want to say how much is A plus B. And here's where, I'm going to erase this, but this is where this geometric interpretation is very useful. We said that the result is 4 plus 5. We're going to see that we can define a rule to add graphically vectors, and the rule says that to add two vectors, you need to go from the head to tail so you will write the first one. Let's say we want to do A plus B, so we go of course from tail to head, and then we want to add B, and B needs to be built from the head of A to the, the tail of B is going to be with the head of A, and then we have the head. So we need to build B actually here. You either take it and move it, or you just count from this point vector B. And how much is vector B? Well, vector B is 1 horizontally, so this starts now counting as our beginning position. So we need to go 1 in x, and then we need to go 1, 3, 2, 3 in y. So it's going to be 1, 2, and 3 in y. So actually, that's going to be this. Why? Because then I can see, there it goes, that's vector B. and this is how much? This is 3, which corresponds to v sub y, and of course this is v sub x, in our case, excuse me, b sub x and b sub y, and b sub x of course is 1, which is what we represented. Let's remove this from here, and let's write a here. And now this is indeed b, that's vector b. Now you might say, wait, is vector b here or vector b is here? Where is vector b? And this is an important thing to understand. We're not going to use vectors that much to actually make a difference, but the truth is that vectors are pointing from the origin to there as a way of representing them. But vectors do not have position. Vectors can be painted anywhere. This vector b here is exactly the same as this vector here. Mathematically, there is no way to distinguish them. And in fact, I can do the same b just here. Provided this has the same magnitude and the same inclination over the horizontal, this vector is the same as this vector is the same as this vector. They are indistinguishable. And that's very important, because when we start to describe motion and we say motion is always relative to the frame of reference, that means to the point of view of the person, if this is my point of view defined by my coordinate axis, it doesn't matter, the vector is going to be the same in any other coordinate system that of course has this orthonormal, right? So the point is going to be, we have the same coordinate, we have different frame of reference, but the vector is represented the same way. The numbers on the coordinates are going to change because I'm going to be describing it in x and y, but maybe some person is defining this as x and y, and he defines them as x prima and y prime, right? And so we say, oh, he's not going to say 3, 2 or 1, 3 in this case. Maybe he's saying minus 3, 4, or what, well, minus 3, 4 could not be. It needs to have the same dimension, right? It could be maybe, I don't know, minus 3 and then something. But the point is, I can describe it in this axis of coordinates, or I can describe it in this axis of coordinates, but the drawing of this vector is exactly the same. And that's going to be very important because the laws of physics needs to be universal. They're going to be independent of the frame of reference, provided, of course, that's an inertial frame of reference, meaning there's no acceleration. That's too technical. The point being is, the vectors do not have position, so don't say, oh, this is different from this. Whenever I say I'm going to build my vector in this point, then you write the x component and the y component, and that is your vector. And that means that by the end of this, I can actually do b and a together, and that's actually vector c, which is the line that joins tail of the first to head of the second. And let's do exactly the same now, but for vectors b plus a instead of a plus b. So what happens when I do b plus a instead of a plus b, right? So we use this. So what I'm going to do, now I'm going to do b plus a. So now in this case, right, I'm going to start writing b. So b goes 1 to x, right, 1 to x, and 3 to b, so in y, 1, 2, 3. So this is going to be vector b, which is kind of what we try to write in here, right? It's the same vector. It's not the same because I didn't draw it that nicely, but it's supposed to be exactly the same. If I take this and move it down, that's supposed to be the same. And then I write a. And how do I write a when I'm adding them together? I write it taking the arrow head as the starting point, as the 0, 0 for this vector. And then I have to move 3, so that means 1, 2, and 3, maybe let's say something like that, right? So that's horizontally. And then I need to move, that's going to be ax, this is b sub x, and this is b sub y. And now we're going to have to write a sub y, which is 1 and 2, so that's going to be 1 and 2. So this is a sub y, 2, right? And so I can build the second one, which points to that. And now the question is, how much is a? Well, this was a plus b. Now this is going to be c equal to b plus a. And so this is c. So how much is c b plus a? I need to go from the tail of the first to the arrowhead of the second. And so I need to join them with a straight line. That's vector c. So what do we see? Well, we just said this vector is exactly the same as this vector. Indeed, they're commutative. We expected that. And I could have painted that vector anywhere else. I could have started building a and b anywhere else in the entire space, and I would have obtained a vector, which if I take the line is always parallel because it has the same direction and it has the same magnitude, which is the length of that arrow. In any case, how to add vectors. This is graphically how to add it, which is important to understand circular motion. How to add them numerically, you just simply add components 1 to 1. So all the x together, all the y together, no more. So let's say now we want to make a subtraction. Now it's saying like a minus b. So how much is a minus b is 3 minus 5, that's equal to minus 2. Is a minus b the same as b minus a? No, subtraction is not commutative. What of course is the same is to say, because this of course is 5 minus 3, which is 2. So it's actually what? Is the opposite, right? This is minus 2, this is 2. So what we realize in fact is that c is equal to a minus b, which is of course the same as saying a plus minus 1 times b, which of course is the same as saying, and now it's an addition, so I could do minus b plus a, which is minus b plus a. And so this is the same as this, but it's not the same as saying b minus a. So again, we have to be careful, excuse me, on how to move vectors. But there's a very interesting thing here. Excuse me. If we see a subtraction, we realize the subtraction is just simply an addition, where the vector being subtracted is just simply minus 1. So this is a good time to, before we go ahead and explain how to do this, we just come back here and express the idea of a scalar product. Excuse me, a product of a scalar. So we want to have a scalar multiplying times a vector, right? And what is a scalar? It's just simply a number of one dimension. So how we do that? If I say how much is 5a, you of course know that that's a plus a plus a 5 times. If this was 5 times vector a, then you're going to know that's vector a plus 5 times vector a. And because we know how to do that, then we can see that we're going to find is that we're going to have ax plus ax of vector a 5 times, and then ay plus ay 5 times. So what is this? This is 5 times a sub x, and this is 5 times a sub y. And then we see immediately what's the result of actually multiplying a vector times a number. What you have to do is just multiply each one of the components individually by the same number. You can see it also graphically. If this is vector a, 5a is going to be taking the vector and putting it 5 times together. And this is 5a. So we see how to multiply scalars. What happens when the scalar is negative? Well, you can find out and do it yourself that if you have, for instance, a vector that it's vector 1, 1, and then this is the vector a, it's 1, 1, okay? And then I ask now how much is vector minus 1 times a? Well, minus 1 times a, according to our formula, is just going to be a sub x is going to be minus 1 times 1, which is minus 1. A sub y is going to be minus 1 times minus 1, which is minus 1. So what's vector a? Minus 1, minus 1. So I can go minus 1, minus 1. This is vector. Let's try to be careful. This is vector minus a. And what I'm saying here is that actually what's happening is I'm just taking the vector and flipping it. But because vectors have no position, I could have written this vector exactly here, overlapping it. So what would be now minus a is exactly the same as a, but just take the arrowhead and pointing in the opposite direction. That's all there is. So every time we multiply times a number, we multiply each one of the components by the number. If that number is negative, each one of the components by the negative number. Graphically, it's just you have a vector, take the arrow and put it in the opposite side of the length of the arrow. And that's all there is. So now we come back to the idea of subtraction. So we can use this idea and then realize that because a minus b is the same as a plus minus b, graphically we were going to have to take a, build it, build b, invert b, putting it, and then you can have the total. But if you want to know numerically, it's just going to be defined, if the vector, c is defined as a minus b, that's going to be a sub x minus now b sub x, and a sub y minus b sub y. So what are we doing? We're subtracting components 1 to 1. Before we were adding them together 1 to 1. Now we're subtracting them now 1 to 1. And in this particular case, that would be 3 minus 1 and 2 minus 3, which is 2, and this is minus 1. And you can try yourself to paint this or make these vectors in an axis of coordinates and see that indeed if you do it graphically, you end up at coordinates 2 and minus 1, meaning, excuse me, you can understand the subtraction as actually that, just inverting one of the arrows and adding them together, and then it becomes pretty simple. The last concept that you should be familiar with, which is going to be relevant for forces, is what we call the dot product or a scalar product. It's called a scalar product because the result is a scalar, right? Not because it's a scalar times a vector, but because the result of product of two vectors is a scalar, meaning it's a number. So that will be written as A point B, and because of this dot, we say this is the dot product. And also because we're distinguishing from the vector product, but that's out of the scope of this course, so we don't even care. And the vector product is defined as, and this is just the definition, as modulo of A times the modulus of B times the cosine of theta. We just want to reflect about this. Does this sound familiar to anyone? So let's say I have two vectors, and let's say I have vector A, and then say I have, vector B. And I'm saying vector B has that and has this angle, which is going to be theta, right? And then I say, what is this? This sounds too familiar. Let's decompose B into its components. Well, we're going to have B sub x, and we're going to have B sub y. How much is B sub x? Well, this is the adjacent. So if I say the cosine of theta, it's equal to the adjacent, which is Bx, divided by the hypotenuse, which is the modulus of the vector B. So then I see that Bx times, the B modulus times cosine of theta, it's equal to Bx. So this is basically Bx, meaning the horizontal component, right? If I come here, I realize immediately this is Bx. In other words, what this is doing is projecting vector B into the x component. But why into the x component? This is important. This theta is not the theta of the direction. It's the theta of the distance between vector A and B. Say that the vectors were, instead of those, the vector was B, this was vector B, and this is vector A. Now theta for B is going to be this. It's not all the way to the angle, it's B. But it can be proven if we instead, let's call it theta prima. It can be proven in this case B times A, well, this is by definition anyways, or A times B because this is also commutative. That's going to be, let's not confuse people, so let's write A times B. So that A dot product B is A modulus B modulus cosine of theta. In this case it's theta prime because we're defining, again, this is the angle between the two vectors. When vector is with the horizontal, this is just simply the x projection. But what about if we define a new axis of coordinates that is completely aligned with vector A? Now this theta prima, it's exactly the elevation of vector B over an axis that I can call, if you wish, x prima. And that axis is aligned with A. So I could do then the same thing I just said before, and then I will realize that this is B sub x. So what is exactly B sub x prima? Because this is prime. So what exactly is this Bx prime? Well, Bx prime is the same as Bx, even if I rotate the vectors. What's happening actually is that I'm calculating the projection of vector B onto the direction of vector A. When vector A matches x-axis, then this is theta is the same as saying is the direction of that vector. But if they don't, then you can imagine there is an axis that is in the direction of vector A, and then this theta prima becomes the elevation with respect to that direction. And again, you're allowed because this is your axis of coordinates. So this is always doing, dot product is calculating the product between the product of magnitude of the first vector times the magnitude of the projection of the first vector onto the second. In other words, it's kind of multiplying the times something times how much of the other vector matches with itself. So we can do a couple of examples, extreme examples, let's say, right? So let's say that the vectors were, so we see it graphically clearly. Let's say that this is A, and then let's say that vector B is that. And I ask, how much is, this is an arrow, not primero, how much is A times B? Well, the first thing I can realize is how much is the projection of B on A? How much is the projection of B on A? How much is the elevation, if you wish, theta prima, of B on A? They're both in the same direction, so there's no elevation, right? So if the vector was here, I'm just closing that angle. So how much is theta prima? That's 0. What is the cosine of 0? Is 1. So how much is that? A product with B is going to just be simply A times B. And what about the case? This is x and this is y, right? And now I take A the same, but B becomes this vector here. Well, I can see now that theta is how much? 90 degrees. So how much is the cosine of 90 degrees? That's 0. So how much is A times B? Well, that's going to be A, B times 0. So that's going to be 0. Why? Because how much is the product of A, magnitude of A times the magnitude or the amount of vector B projects onto A? How much of the shadow of B, if you wish, from above, right, illuminated from above, produces on A? Well, it doesn't produce any shadow. So there's nothing of B on the direction of A, therefore the product is 0. And anything in between, of course, will be modulated between 0 and A times B modulus by cosine of theta that's going to go from 0 to 1. That's the idea of the dot product. Why is this relevant? Because we will see in the chapter of forces are vectors, and we will see in the chapter of energy that we can describe work as the force times displacement. Displacement has direction. It's not the same to go Orlando, Miami, then Miami, Orlando, then Orlando, Bahamas, or whatever, right? And also, force is going to have direction. It's not the same to push the sofa to the front, like in front, to push the sofa towards the side, right? It's not the same. If you want to get closer to the TV and TV is in front of you, you have to push it towards the TV. If you push it sideways, even if you push it with the same strength, that's pretty silly. So we see the force also is going to have a vector to describe it. And so we're going to see that work is going to be defined in that case, and we will see it again. This is not relevant now. It's just the force times displacement. What is important here that this is going to be a dot product. So what we're going to be asking is how much of the force aligns with the direction of the displacement. And if you have a force that doesn't align with the displacement, then you're not doing any work. If you have which will be this case, if you have a force that does not it does align completely with the displacement, then you're doing the maximum amount of work, which is to say how is more efficient. And this is what we're discussing. If the sofa needs to move towards there and I'm pushing towards there, these two vectors are going to be orthogonal. I'm not achieving anything. 0, result of work 0. But if my goal is to get there and I'm moving there and I'm pushing exactly there, then I'm maximizing my force effort into the direction of the displacement. The work is going to be maximum, which because this is going to be 0, that's going to be 1. They're both in parallel, they're both aligned, so work is going to be maximum. We'll see these ideas again in chapter probably 4 or 5. For the time being, let's understand product vector dot product is the result of multiplying the magnitude of one vector times the projection or the magnitude of the projection of the other vector into the direction of the first vector. And being commutative, you can say that this is A times B, but you could also define B times A. That's up to you. Just watch out for the sign with the angles.